Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So, good morning to all of you. And today we'll continue our course on parallel computing. So, previously, what we have discussed on the chapter 1 is the advance of microprocessors. Okay, so because of the physics, they cannot increase more the frequency, the frequency of the processor, so that they now geared toward the multiprocessor. It started in 1996 by IBM, core chip, and then we have now the 64 cores and 128 cores and so on. Okay, so in chapter 2 we'll discuss on parallel hardware. So we'll focus on hardware first. Okay, then later on chapter 3 will be on parallel software. Okay, so this is the outline of my presentation. Okay, some background. Let's refresh it back. What is the von Neumann architectures? Okay, what is process? What is multitasking? What is threads? Okay, and then why it's need to modify the von Neumann model. Okay, the improvement or modification to the von Neumann models. So you can see here the improvement is on the catching. Then cache mappings, how we map the cache with the main memory, and then the advance of virtual memory means that part of your hard drive now can be treated as main memory. And then we have instruction level parallelisms, like hyperthreading. Intel and AMD do. They can run multiple programs at once. Okay, so if you have hyperthreading, then you can run 2 instructions at once and so on. Okay, and even can have 7 instructions at once, and depends on your chip architecture. And then hardware multi-threading. Okay, so within one core, okay, they can create 2 threads and so on. Okay, then we go to the parallel hardware. What is the SIMD systems? Single instruction, multiple data. So you have single instruction and then multiple data. Okay, so the example is vector processors and GPU. So GPU is in here. Like I mentioned earlier, for example, you want to calculate the shade. Okay, so for every object, if this light source, okay, so then you want to calculate to every pixel here. Then you create for single instruction, okay, but multiple data, multiple pixels. Okay, most of the parallel computing is using this one. So you are working on single instruction, but you do for multiple data. But it can also multi-instruction, multiple data. For example, shared memory system and distributed memory system. You can apply multi-instruction, different instruction for different data. Okay, so yeah, so you have 2 types here that we learned earlier, which is the shared memory and distributed memory. And we have interconnection network. Okay, this is also important. Maybe I'll put here the von Neumann architectures. You have CPU, okay, and then you have memory, okay, and then you have I/O, okay, and then interconnection. So there are 4 elements of von Neumann architecture: the CPU, I/O, and memory, as well as interconnection. So this is also important. Okay, the interconnection also important because no matter how fast is your CPU, but if the interconnection and the memory cannot cope with the CPU, then it will slow down. Okay, it will slow down your computational experience. Okay, as well as the I/O, we know that the I/O is the slowest. Okay, for example, you want to print some page. Okay, so like 1 page 4 seconds, so you can see is very slow compared to the other types of memory like Ethernet card, like yeah, maybe keyboard and so on. Maybe 1 millisecond, 1 nanoseconds. Okay, it's faster, but still I/O and memory normally is slower than the CPU. Okay, so that's why we need to have some modification here. Okay, to the von Neumann architecture. So here on the parallel hardware, the interconnection also play an important role. Okay, how do we interconnect the shared memory? How do we interconnect the distributed memory, and what will be the latency and bandwidth? Okay, the latency is the times to start, okay, before steady state, and the bandwidth is the the width that you can, the amount of data that you can send within one time. Okay. Then we will discuss on parallel hardware is cache coherence. What does it mean by snooping, cache coherence, directory-based cache coherence, fault sharing, and then the last one we'll do shared memory versus distributed memory in more details. Okay. Okay. After this, after we understand the parallel hardware, then we can move on to the parallel software. Okay. So let's start for the same some background. Okay, so let's see here. This is so the starting from the serial of if you have serial, then you have parallel. If you can see here, parallel is like this. So you have one line only. Parallel, you have multiple line. Okay. So how to move it faster? Serial is in a way that this is cheaper because you only need one copper line here. Okay, if you are sending the data, for example, parallel, you need multiple lines here. Okay, so that's why to compensate the slowness of serial, normally they put higher speed, like in USB, universal serial bus. Okay, this is serial only. Okay, so you have only positive, negative, and data plus and data minus. Okay. So this is serial. Parallel, it was gone long time ago because it's too complicated, maybe more expensive, and although this has faster, maybe if you want to go to the design later on, but still this is simple. And when you put the speed high enough, then it can compensate. Okay. The other things on the CPU also there are other things. Okay, on CPU front, you have a single thread performance and multiple thread performance. Okay, for example, the Apple M1 CPU that using RISC, it has the highest single thread performance. Okay, so the designer is very clever, because most of the time you're only working on a single program, like open Microsoft Word, you focus on typing only on Microsoft Word, for example. Okay, this you can assume that it is single program, so you just need maybe single thread. Okay, at the background, of course, there are some spelling checker and so on and formatting. Okay, but you can do something like interleaving, okay, rather than overlapping. Okay, so you get the feel that whenever this is faster, you get the feel that the computer faster. Okay, this is represented by the CPU clock frequency. Okay, 1 gigahertz is the minimum for Windows 11, then up to 5 gigahertz. Okay, the latest Intel 5 gigahertz, but normally they stay at 4. Okay, the optimum is 4 because the heat dissipated is not as much as 5 gigahertz. 5 gigahertz, maybe you need some special cooling. Okay, there are some world record, it can go also to 7 gigahertz, but it needs special cooling to the CPU, otherwise the CPU will burn. Okay, but so this one will contribute to the single thread performance. Okay, the clock frequencies here. Okay, it will contribute to the single thread performance. You achieve faster, so you write the program on 1 gigahertz, you run it on 5 gigahertz, you feel that it is 5 times faster. Okay, I repeat, if you write a program in 1 gigahertz and run in 1 gigahertz, and then you move to 5 gigahertz, you will feel that the program 5 times faster. Okay, so the multiple thread is whenever you have multi-core, 2 cores, 4 cores, okay, and so on, 8 cores and so on. So this is multiple thread performance, similar like this. Okay, so you want to make the lines more lines for the processing. Okay, you want to have more line for the processing. Okay, so but on the serial hardware and software, a single job run at a time. Okay, so computers only run one program at a time. You have the programs, program have the input, put in the computers, and then produce the output. Okay, so the classical for Neumann architecture consists of main memory. So this is the first one. Okay, first element. CPU, of course, this is the second element or processor or core, and interconnection. This is number 3, and number 4 is actually we have some kind of I/O. but it's also connected to the memory. Okay, so you have CPU, but the very basic is this one. Okay, and then you have memory here. Okay, interconnection and then memory. So if you have I/O, you can plug in here. Okay, you have the I/O here. Okay, so the CPU has arithmetic and logic unit registers. This is also some kind of memory, the very fast memory, because it resides in the CPU itself. Okay, you have control registers. Okay, you have interconnects and memory. Of course, you have address and the contents. Okay, you have the address as well and the contents. So if you have 32 gigabits, 32 bits addressing, okay, so you can only install maximum 4 gigabytes of memory. Okay, maximum will be 4 gigabytes of memory. Okay, because this is the maximum of 2 to the power of 32. Okay, so that's why we have no more 32-bit processors. It move on to 64-bit processor. It can handle up to 2 to the power of 64. 2 to the power of 64. Okay, so now let's see one by one the architecture. So the main memory consists of location. Each of is capable of storing both instruction and data. So if you have memory here, the memory, some part you can assign for your instruction or program. Okay, some part, of course, you need to have the data. Okay, so the instruction, for example, x equal to x plus 1. So this is additions. Okay, for example, is the instruction, and then the data is on the x. Okay, x is the data. Okay, so you have instruction and you have the data. Okay, of course, for instruction, you have line of code, line number 1, 2, 3, 4, 5, and so on. Okay. So every location consists of an address, which is used to access the location and the content of the location. Okay. So in here, yeah, so the memory technology also, as I mentioned earlier, it can become the bottlenecks. Okay, so that's why we have single data rate, we have double data rate, the double data rate 2, double data rate 4, 3, double data rate 4, and then the latest one is double data rate 5. Okay, so only on the new Intel chipset, okay, and the new AMD later on next year. Okay, so if you go along here, it will be faster. Okay, it will be faster to cope with the CPU speed. Okay, otherwise, later on we'll see the example. If the CPU is fast but the memory is slow, so the CPU need to wait. Okay, so it will be waste of time. Okay, so you have different form factor also for the memory. Currently we have yeah, this is DIMM, double insertion memory module, and we have also single instruction SODIMM here. Okay, for the laptop. Okay, so this is the memory. The CPU is divided into control unit and arithmetic logic unit as the bare part. Okay, the control unit is the responsible for deciding which instruction in program should be executed. So this, we have the boss as well, and LU is the responsible for executing the actual instruction, the worker. Okay, so we have two processors. This is CISC processors, but also there are now we have RISC architecture. Your ARM, when you have your handphone from Huawei, from Samsung, and Xiaomi, for example, normally they license the ARM microprocessor from Qualcomm or develop their own. And we have another architecture which is RISC-V. Okay, RISC-V architecture. So this is free to license. Okay, this is you need to pay. Okay, so this is paid architecture. So the design is you need to pay to license the architecture. Okay. So if you have any questions, so you can interrupt me. Okay. So yeah, so CPU has registered. It's very fast storage. This part of the CPU, but you cannot put more. Okay, because of the what you call the memory pyramid. Okay, so the memory pyramid here. Okay, on the top one you have registers. This is the fastest. Okay, you have L1 cache, L2 cache, L3 cache, and the main memory. Okay, on the second level here you have hard SSD, fastest, then hard drive. Okay, CD-ROM or DVD-ROM, for example. Okay, and on the last one you have a backup tape. Okay, you have tape here. Okay, as you go along here, the capacity will be bigger. Capacity will be bigger. Speed will be slower. Okay, and price will be cheaper. Okay, price will be cheaper. Okay, so that's why we don't put all in here, because it's expensive. Okay, and the capacity is limited. Okay, because of the expensive. Okay, so yeah, so you have CPU, memory, input and output. You have control bus, address bus, and data bus here. So you can see like 3 tracks in line. Okay, for the control, address, and data bus. Okay, so a von Neumann architecture execute a single instruction at a time, and each instruction operates only on a few pieces of data. So few pieces means you can see the simplest one. For example, on the von Neumann architecture is reflected the assembly language. Okay, for example, what if you want to add here a equal to x, a plus b plus c? So first you need to add x equal to x plus a, you equal to 0, then x equal to x plus b, x equal to x plus c. So 3 times to implement this one. Okay, because you have only a limited pieces of data to do the or to operate on one instruction. Okay, so when data or instruction are transformed to the CPU, we sometimes say the data instructions are fetch or read from memory. So this is fetch or read. Okay, so remember that the memory has the program or the instruction as well as the data here. Okay, so this is fetching the data. Okay, so you need to go to interconnection bus. Okay, then you go to the CPU. If you store, okay, the other way around, if you store, so we write here from the CPU, the result, store it back to the memory, and later on, if it requires, the memory also can write back to the hard drive or SSD. Okay, you can write back to the result to hard drive or SSD. So you can see several process here. Okay. Okay, so what will be the von Neumann bottleneck? The separation of memory and CPU is often called the von Neumann bottlenecks, since the interconnect determines the rate at which instruction and data can be accessed. So what will be the bottleneck is this one. Okay, the bottleneck will be the interconnect connection. Okay, because we have limited interconnection. Okay, so for example, you have the factory CPU, you produce more goods, okay, then it need to store in the warehouse, in the memory, okay, but you have only one truck, okay, so of course you need to have several trips, okay, to move all the goods into the warehouse, okay, if the warehouse is full, then you need to wait first, okay, then maybe you go to another second warehouse, which is the hard drive, okay, you need to transport also to the second hard drive, okay, so this one become the bottleneck because the road is limited. Okay, if you have multiple track, for example, still you need to queue. Okay, you need to have you need to queue. Okay, because you have the bottleneck here on the interconnection. Okay, the interconnect will be the bottleneck. Okay, so let's see the example. So let's see now. The von Neumann bottlenecks. Okay, so for example, here we have 3 gigahertz computers and with 8 cores, and then one core can do 16 floating point operation per second. Okay, so then you can see here you have 300 when you multiply here 3 times 10 to the power of 9. Okay, and multiple by 8, multiple by 16, and you have 384 gigaflop per seconds. Okay, so you can see here the maximum performance, the peak compute performance is 384 giga floating point operation per second. Okay, but remember that this will be the bottleneck. Okay, why is it the bottleneck? Okay, because of the data rate limitation and as well as the memory limitation. If you see here, the warehouse is limited. Maybe you cannot have all the result from the CPU. Okay, all at once. So you need to wait first. The CPU need to wait until the warehouse is free. Okay. So let's see here the simplified model in order to establish an upper bound on performance. So what would be the maximum performance? Okay, means that we cannot go beyond this one. For computing a dot product is just the multiplication, okay, multiplication operation, okay, of two factors, which is u and v, containing n double precision numbers stored in main memory, okay. And then because this is the upper bound, so we'll never go faster than what the model predicts, okay. So let's see here, we have main memory. Okay, so the maximum is 51.2 gigabit per second. So you can see here, the peak transfer rate of DDR, I'm not sure, maybe DDR4, this is 51.2 gigabit per second. Okay, but compared to this one, at least 6 times giga floating point operation per second. Okay, so you can see now the, even without calculation, you can see here, there's a bottleneck. Okay, the memory cannot handle the speed of the computation. Okay, so it will be, the upper bound will be determined by this one, the slowest, the slowest part. Okay, the upper bound here will be determined by the slowest part. Okay, so let's see the calculation. So for example, here you have the dot product, doubles mean, yeah, you can have 64 bits or 32 bits, okay, in one go. Okay, so let's see here, integer I, dot product is, you just multiply the UI with VI and then you add into the sum here, okay. So let's see, the n is to the power of 30, an example. So this is 30 bits, for example. So the computation times is requires will be 2 gigaflop, this one, 2 gigaflop, okay, divided by 384 gigaflop. So requires 5.2 milliseconds. Okay, so because the capacity of the 8 cores, 3 gigahertz and 16 flop per second, okay, of the CPU. Okay, so you divide this one, so you have only 5.2 milliseconds. Okay, very fast. Okay, yeah, because the total operation will be 2 times this one. Okay, multiplied by this one. Okay, operation will be 1 and 2 here, so 2 times operation. Okay, 2 times 31 will be 2 gigaflops. And data transfer time will be 16 gigabytes. For example, you have 16 gigabyte of memory, okay, of memory, and data rate will be 51.2. You can see here 312.5 is larger than this one. Okay, this is 5.2 milliseconds. This is 302.5 milliseconds, because the amount of data to be transferred is 2 times 2 to the power of 30 times 8 byte. Okay, because you are in bit. Okay, 8 bits, sorry. Okay, so you have 16 gigabytes, sorry, 8 bytes, so you have 16 gigabytes. So the execute time will be larger than equal to of the maximum between this one. Okay, you can see the slowest part will determine the upper bound. Okay, because you cannot go faster. Okay, you cannot choose this one. Okay, it will be determined by the slowest one. So if you are on the team group, for example, you are running on a team. Okay, so the result will be determined by the slowest one. Okay, so for example, your instructor said, please run in group. Okay, you can run faster, but your friend only can run very slow, for example. Okay, then it will determine by your friend's speed. Okay, overall running time. Okay, so the achievable performance is 6.4 gigaflop per second. This is less than 2% of the peak, which is this one. Okay, which is this one. Okay, 2%. So because the dot product is memory bound, so no reuse of data. Okay, you can see here, this is the upper bound. Okay, although we have faster processors, but if the memory is slow, the interconnection is slow. Okay, then yeah, the peak transfer rate here is determined by the bus also and the speed of the main memory. Okay, the determined by interconnection and also the peak transfer rate of the main memory here. So when you transfer this one or transfer back here, the speed is 51.2, but this one 384 gigaflop per seconds. Okay. So from here you can see that there is some bottlenecks. Okay, then the next one will be how can we overcome the bottleneck. Okay, there are many methods okay, to overcome the bottlenecks. Okay. But before we move on, we'll go to the basic of OS first. Okay, so what is the difference between process, multitasking, and threads? Okay, so we have the hardware, the four Neumann architecture. We have CPU, and then we have memory. Okay, and then we have the I/O. Okay, with the interconnection. Okay, the one that put the operation here is the operating system, the one that manage all the resources. Okay, so how to put the program into the CPU, which one to load first, and so on. Okay, it include let's say the CPU scheduling, okay, scheduling of the CPU, I/O scheduling, okay, and then memory management and other resources management, okay, and others. Okay, you have the date and time, real-time clock, and so on. So it's provided by, managed by the operating system. Okay, so when a user runs a program, the operating system creates a process, so which is an instance of a computer program that is being executed. So for example, you double click the PowerPoint, it will show if you go to task managers. Okay, if you go to task manager, okay, let me see whether I can go to task manager here. Oops. Yeah, so if you go to task manager, okay, then you can see the process. So this is the process. Okay, so this is the process, and it has what you call the process ID. Yeah, so it has the process ID. Oh, it's not showing here. Yeah, okay, so this is the process, and you have the threads. You can see from here the CPU, for example. I put in the CPU. You highlight here, you can see here. This is so let's see. This I have logical processor 8 cores. Okay, but one core can run 2 threads at the same time. So logically you have 16 cores. Okay, but you have 8 cores on the physical processors. Okay, and then you have the L1 cache, okay, L2 cache, L3 cache. Okay, and then you can see here you have process. I'm running now 308 process with 52813 threads. Okay, and the handles, the IO handles from Microsoft. And you can see here also, if you go to the Linux, okay, you can see also the process ID here. Okay, I have not run anything on Linux, so I cannot that not much program here on Linux. Okay, you can see top H. I want to see the threads. Okay, so there are the threads here. So 7 total threads, 7. Okay, 1 running, 6 sleeping, and so on. Okay, so this is the process and the threads. Okay, okay, so let's move on. Yeah. Yeah, so the component of process. So what would be the component of process? The executable machine language. So the process has at least this one, process control blocks, program, data, and then you can have here the shared resources. Okay, shared resources. If you want to communicate with other program or other process, you can share it with this one. Okay, but mainly you have process control blocks. Okay, and you have program, the executable machine language program. So this is program. A block of memory, executable code, call stack and heap. So you have also stack here, stack and heap for calling function, passing the parameters, and so on. Okay, and descriptor of resource that always has allocated to the process, file descriptor. So you have also from here, you have in OS you have process manager. Okay, so it has process table, IO table, memory table. So you know that this process will occupy which one, this process will occupy which part of memory, and so on. Okay, as well also have security information, whether you're set or not set. Okay, and information about the state of the process, whether it's running. Okay, it is blocking. Blocking means doing the IO, or sleeping. Okay, what's the term for sleeping? Suspend. Okay, suspending. Okay, running, blocking, or suspend. Okay, so this is the process. So every computer has process, whether it is Linux, whether it is Windows, it has the process. Okay, So most modern OS are multitasking, means give the illusion that a single processor system is running multiple programs simultaneously. So the easiest one is you can think like yeah, this one, round robins. Each process takes turn running time slice. After its time up, it waits until it has turned again. So the blocks. So say that you have three program. Okay. So what you do is you attend to program A for 1 milliseconds, very short. Okay, 1 millisecond. Then you go to the next one, 1 millisecond, go to the next one millisecond, then come back to process A, 1 millisecond, process B, 1 millisecond, process C, 1 millisecond. Okay, if process A has finished, for example, here, then you go to process B. Okay, then process C and continue. Okay, so this is multitasking if you have only one processors running. Okay, if you have multi-processors, so you only can do interleaving here, interleave. Okay, but you get the feel that it looks like you are what you call, you open multiple programs. Okay, so it looks like, for example, you have you open PowerPoint here and Microsoft Word, and this is Chrome, for example. Okay, so one milliseconds it do the round robins. Okay, it looks like you're opening 3 programs at a time. Okay, it looks like that you are opening 3 programs at a time, and because this is, you have very short time slice, so you don't get the feel that it is lagging. Okay, unless if, for example, you have 1,000 process running at a time. Of course, you can see this is wait. If you have 4, for example, here D, then you need to wait here. Okay, you need to wait, then only it can go back to your program A, so it will be slower there. You can feel slower, 4 milliseconds, then you go back here, rather than here 3 milliseconds total, then you go back to your first program. Okay. Okay, so this is multitasking. Then what happens if you have multi-core? If we have multi-core, not only we can do interleaving, but we can also do overlapping. Okay, so when you have A, B, C, for example, because you have 2 cores, for example, you have 2 cores. Okay, then you have run A, then you can run B at the same time. Okay, and then A and C can share. Okay, then here C, go to A again, go to C again, and so on. Okay, so you can do overlapping. Okay, some process can run overlap. Okay, but this one need to be supported by the operating system. Okay, the operating system, remember, they have the scheduling algorithm, so it need to be supported by the operating system. Okay. Okay, so let's move on. The second one is threading. Okay, so threading provide a mechanism for programmers to divide their programs into more or less independent tasks with the property that when one thread is blocked, another thread can be run. Why this block? This is doing an IO, then another thread can be run. Just for an example, okay, so you have, while you are doing, let's say you open Microsoft Word, okay, Microsoft Word. Okay, you open Microsoft Word, then suddenly you want to print. Okay, what it will do, this is the program. The first one, you go to editing, still editing, and second one you can open for printing. Okay, so while editing here, then you can do printing here at the same time, printing in the background. Even in the background, you can create another thread. So this is first thread for editing, and this is the second thread for printing. Okay, printing is IO bound operations because it takes a longer time. So, but because we are creating 2 threads, okay, so we don't need to worry about the waiting for the printer. If you don't create thread, what will happen? While you are printing, you need to wait until the printing is finished. Then you only can edit. Okay, so that's the difference between one thread or you can create multiple threads. Okay, and threads are lighter weight than the process, faster switching. So what will happen here is you have here process. Okay, process. You have, of course, you have process control blocks. You have the memory allocated for you, and then you can have your thread control blocks, and you have program, you have data. You can create another one, program and data. Okay, you have program and data here. Okay, and so you can see here it belongs the thread 1 and thread 2 can access to the main thread memory. Okay, so main process memory. So that's why, although you are doing editing here, okay, but you can capture this one first and print here, because you can access the same information, okay, the same data, because you can access the same memory location here. Okay. Yeah, so the hope is that when one thread blocks because it's waiting on a resources, another will have work to do and can run. So you can have the optimum CPU utilization. Okay, the CPU is not idle, but still you want to maximize the CPU. Okay, so visually you can see like this. If you have, for example, the example of this one also, like when you do uploading and also downloading, for example. Okay, it create actually multiple threads. Okay, it can create multiple threads. For example, if you go to any website, okay, maybe one thread will download the image. Okay, one thread will download the text, and then at the end they combine image and text. Okay, to form the complete website web page. Okay, so you can see from here, the thread can be used for many things. Can be uploading when you do, for example, using some kind of download managers. You can download, or you have 1 GB file, for example, you can split into 4. Okay, so you can assign thread 1, thread 2, thread 3, thread 4. You download part by part here. Okay, and at the end combine into 1 GB. Okay, so this is also if you get the faster download, you can do like this. Okay, you can run multiple download at once actually. Okay, and then at the end it combine. Okay, so yeah, so starting a thread is called the forking, because you can see this fork. Okay, fork into two lines of operations, and terminating a thread is called the joining. Okay, right? Any questions so far?
No, sir.
Okay. Okay, so if no question, then I'll spend just another 15 minutes, okay, to move on to the modification of the von Neumann models. Okay, don't worry, this chapter has 100 pages. Maybe we need 2 weeks, okay, to finish. Okay, I'll do it slowly, inshallah. Okay, as we know, what happened is this is the von Neumann architectures. Okay, CPU, and then we have the memory. Okay, and then we have here the I/O. Okay, and the interconnection and the memory, or even I/O, provide the bottlenecks. Okay, so now how can we modify the von Neumann architectures to be faster? Okay, so many solutions are targeted at reducing the problem of the von Neumann bottleneck, but many also are targeted at simply making CPU faster. But remember that when you make the CPU faster, but this is slower, still it will be determined by the slowest. Okay, it will be determined by the slowest. Okay, the upper bound, remember, it will determine by the slowest. Okay, by the slowest part. Okay. So the modification of von Neumann model is include caching, okay, caching memory, and virtual memory, and of course low-level parallelisms. Okay, so you can run also multiple instruction at once. Okay, so let's see on the basic of caching. Okay, where's the cache? Okay, you can see from here. Yeah, from this one. Okay, you can see this one. You have level 1 cache, level 2 cache, and level 3 cache. Okay, level 1 cache is only 512 kilobytes, level 2 cache is 4 megabytes, and level 3 cache is 32 megabytes. Okay, and you have here, you can see the base speed is 3.6 gigahertz, and the socket is only one. So because I only have one socket, and it's not server motherboard, only consumer motherboard, so I only have one socket, and the core is 8. Okay, but one core can run 2 threads at the same times, so that's why the logical processor is 16. Okay, the logical processor is 16, so that's why you can see there's yeah, there is 16 here. Okay, there's 16 graph here, the processor utilization. Okay, and then in terms of architecture, this is the CPU. Okay, CPU number 1, and then you have L1 cache, you have L2 cache. Okay, um, okay, yeah, and then you have L3 cache. Okay, L3 cache normally combined. Okay, so you have C, L1, L2, L3 cache. Okay, combined. Okay, that's why the L3 is bigger. So it provides a shared memory between all cores. Okay, it provides shared memory between all cores. So you can see here L1 belong to C, to person number one here, person number two. L2 also belong to person number one or number two, but L3 belong to all. Okay, belong to all. This is Intel architecture. There's the AMD architecture. It has provided different things. Okay, C1, C2, C3, C4. It has different L1. Okay, it has different L1. Okay. Okay, but it has sorry, this L1, but it has the same L2 for adjacent processor, like this. Okay, so L1 is shared between C1 and C2. L1 is shared between C3 and C4. Okay, and then we have L3 cache. Okay, from here they go to interconnection bus, and then we go to the memory. Of course, the memory will be bigger. Okay, as mentioned earlier, this is 512 in my computer kilobytes. This is 4 megabytes, and this is, what was it? 8 megabytes, I think. Sorry, 32 megabytes. Okay, 32 megabytes, and computer memory is 32 gigabytes in my case. Okay, 32 gigabytes. So you can see here the difference. This is mega and this is giga. Okay, but why we do this one? Okay, or why do you now introduce cache here? Why we introduce cache here? Okay, so cache is a collection of memory location that can be accessed in less time than some other memory location. Okay, remember the pyramid of memory. So this is the first one, second pyramid, and third pyramid. Okay, if you go up here will be faster, but it will be smaller in size and expensive. Okay, so that's why it's smaller. Okay, so you can think that just a smaller size but faster. Okay, smaller and faster as we go up. Okay, smaller but faster. Okay, so a CPU cache is typically located on the same chip. Okay, so when you design the CPU, you design also the L1, L2. So that's why you can see here, this is the Intel architecture. You have separate L2, but AMD architecture, it has what you call combined L2 cache. Okay, for adjacent processors. Okay, adjacent CPU. Okay, and then much faster than ordinary memory chip, because you don't need to go out 1, 2, 3 and then go out to the memory to read. Okay, but we create some solution, but we create also another problem. Once we have a cache, an obvious problem is that deciding which data and instruction should be stored in the cache, because the memory combined into two. We have the data and instruction, or the program itself. Okay, like PowerPoints and so on. And the data is like the file that you are working on. Okay, that will be the data. Okay, so how do we do this one? Of course, we have some algorithm how we do this one. Okay, we have to decide which one is required, but most probably we use the principle of locality. Okay, say like this: if I walking toward that one, okay, I'm walking to the right. Okay, I can predict that I will go here on the next one. Okay, or I can predict maybe this one. Okay, it will not turn suddenly. It can happen, but most probably it will continue to the path like this. Okay, so that's why we have the principle of locality. Most probably that you will need the data or instruction closer in time or closer in space. Okay, so I can predict that I will need this one. The position will be here and here. I can predict, the CPU can predict. Okay, we have one part in the CPU called memory management unit. It try to do the branch prediction, try to predict which data that we require and so on, and then move to the cache. Okay, move to the cache. Okay, yeah, to explain here. Yeah, so we have the principle of locality. So accessing one location, whether it is instruction or data, is followed by an access of a nearby location. So this is the keyword. Okay, the location, whether it is in time or temporal or in space. Okay, spatial locality. Okay, whether it's in time or in space. Okay, so let's see, for example, here. Okay, as you can see here, this is I0. So suppose that you have uh, a buffer, okay, z buffer here, 0 until 999 here. Okay, so you can see here, I equal to 0, I equal to 1, I equal to 2 until I equal to 999 here. Okay, you access the value of z variables. Okay, so the arrays are allocated as block of contiguous memory location. The term contiguous is actually um, you don't need the what you call the uh, uh, you don't need continuous because you have the page table later on. I will explain. Okay, but assume that you have continuous memory location here from 0 into 999. Okay, the location storing Z1 is immediately follow the location of Z0. So this is Z1, Z0, and then Z1, Z2, and so on. Those as long as I equal less than 999, the rate of Zi is immediately followed by the rate of Zi plus 1. So what does it mean? It means that before you even need this one, we can load this one to the cache. Okay, before you even need this one, okay, the Z2, you can load to the cache. Okay, so you have cache, you have memory. Okay, but remember that this is smaller but faster, and this is bigger but slower. Okay, the bigger but slower. Okay, so what you need to do, instead of you are reading one by one, read one by one like this, one by one like this, it will you read in one go, because you can read in one go here like this, and move to the cache the whole. So at least you can have, for example, Z0 until Z9. 10 variables, okay, 10 elements of your matrix, okay, Z0 to Z9. Okay, you don't need to read Z0, Z1, Z2, Z3 until Z9. So you read in one go, put into the cache. Okay, so you do multiplication faster. When you need another one, you catch again. Okay, so this is, for example, Z10 until Z19. Okay, so you continue like that. Okay, replace the cache here. Okay, and then with the data that you want. Okay, so you can see here, we can sometimes also the compiler can optimize this one. Okay, so it can instruct that please put this one into the cache. Depend on the cache size, it will calculate the cache size. Okay, and then it try to load as much as it can. Okay, the question is, for example, let's say you don't need, for example, Z18 and Z19, for example. Okay, that's fine. At least you have 8 variables is do the operation on 8 variables, and 2 can be discharged. Okay, still faster rather than you are doing 8 times, doing from the reading from the CPU to the memory 8 times. Okay, so overreading, that's fine. Okay, but so it still it will be faster. Okay. Okay, so so in order to exploit the principle of locality, the system used an effectively wider interconnect to access data and instructions. Okay, and memory access will effectively operate on blocks. So rather you go one by one. Okay, one line, one by one line. You can read on the wider interconnects to access data and instructions. So instead of 1 bit, for example, you go for 8 bits at a time. Okay, 8 bytes at a time. So you can load 8 variables at one time, for example. Okay, rather than you read one variable at a time, now you can read 8 variables at a time, but it needs to have a wider interconnects. Okay, so a memory access will effectively operate on blocks of data rather than single data or instruction. Okay, so block of data, okay, rather than single data. Okay, instead of single instruction or individual instruction. So these blocks are called cache blocks or cache lines. Okay. So a typical cache line store 8 to 16 times as much information as a single memory location. So for example, here you can divide it into 16 here. So you can divide, okay, if you have 16, okay, 16 cache, okay, and the memory you have 9,000, for example. This is, for example, the Z on the memory. Okay, it has 1,000. Okay, so let's see, 1,000 divided by 16, 62.5. So at least you need to read 63 times. Okay, 63 times to read the one block of memory compared to 1,000 times. Which one will be faster? Of course, this one. Okay, it's because you only need to read 63 times. Okay, this is because it's 62.5. Okay, so you need to read 63 times. So the last cache, maybe you don't need some of the memory, only occupied half. Okay, but that's fine. Okay, but you compare this to 1,000 times, still faster. Okay, how much faster? So if you divide roughly, so 1,000 divided by 63, so roughly it is 15.8 times faster. Okay, so you can see the benefit of the cache memory. Okay, yeah, so the cache is usually divided into levels. Okay, and I will stop at the cache. Okay, I will continue on Thursday, inshallah. Okay, and variable stored in level 1 cache will also be stored in level 2 cache. So there's a copy here. Okay, if they have a rabbit here, there will be a rabbit here because this is part. Okay, this is also will have the rabbit here. Okay, this also will have the rabbit. Even in the memory, of course, there will be the rabbit there. Okay, so you just copy which one that you need. Okay, if you go up here, it will be smaller, but faster. Okay, you can see the pyramid. If you go up, it will be smaller, but it will be faster. Okay, so let's see the cache hit. What in by cache hit? So for example, you want to fetch the X. Okay, you want to read the data X. Of course, in the main memory, the 32 GB have also X. But if you go read here, it will take time. Remember that maybe 1 nanoseconds. Okay, here maybe you need 1 picosecond. Okay, faster, 1 picosecond, because it's closer to the CPU. Okay, it's closer, and even it is on the same chip there. Okay, so L1 you have X here, so you can catch hit. Hit means you don't need to go down. Okay, you need to search down until the memory to find X. Okay, so this is catch hit. Okay, so but if you don't have the X, for example, here fetch X, oh, it is not there on L1 cache. It is not there on L2 cache. It is not there on L3 cache. It is there on memory. So you don't have any choice. You need to read from the memory. Maybe it takes longer time. Okay, it takes longer time. Okay, so this is miss. Okay, cache miss, because the variable or that you need, it's not there on L1 cache. It can happen also. For example, you have L1 miss. Okay, but you can have L2 hit. For example, the X is already here. Okay, so you can replace this one by X. Okay, and read there. Okay, or you have X and R1 requested, so you can read or replace these two with X and R1. Okay, so you predict that you need X and R1 at the same time later on. Okay, so this is L2 hit. Okay, so I think I'll stop here. Okay, if you have question, then you can ask me.